Good evening. The question of whether a random angle can be trisected using only an unmarked ruler and a simple compass has baffled and frustrated mathematicians for countless years. The theorem I have put forth herein meets and exceeds the parameters this problem poses. It is the Soli Deo Gloria theorem. Further, by extension of the basic construction, one can exactly subdivide into equal arcs any given random angle. This is the extension corollary to SDG. Within this document, the curious will find examples of various trisections, even a quintsection. You will also find the algebra to be very straightforward, as it does not need or require to pit against the base 10 numeric system that we use. Please be advised, however, the methodology of construction will not be kind at all to the sloppy or the otherwise imprecise geometer. As you use this method, you must hold to the highest standards of precision and do so patiently. As God has blessed me with this method, may He also mightily bless you with even more. The theorem itself: for a given angle randomly chosen, tangent circles of equal radii set along a common line that is collinear with each diameter will create an arc at the third radius by drawing two lines to the initial angle's endpoints as exactly 1/3 its arc. And that's measure, we use alpha in this case, which is equal to 1/3 of AOB. Okay. In other words, this right here is our angle, and these orange lines are the trisectional lines that will be created. Where AOB is the initial angle itself, resulting corollary to SDG theorem. In a like manner, the endpoints of each radius will create arcs of equal measure on the arc of the original angle. For n, a member of the integers plus, measure angle alpha is equal to 1/n times the measure of the initial angle itself. The process is really pretty straightforward. It's actually very simple. You construct any angle of any size you wish. Make it completely, totally random. Don't measure it. You don't need to. Construct an angle bisector that goes through the vertex, obviously, and then extends into space. And along this, we will draw equal radius circles for as far out as you wish to go. Note the angle bisector is also the diameter of the initial circle itself. Using the exact same radius, mark the next center, circle 2, on the angle bisector. This ensures the next circle is tangent to the initial circle with a point of tangency on the angle bisector. For the center of circle 2, draw two lines, L1 and L2, from the two intersection points of the initial angle to circle 1. That's A and B here, the intersection points. Bring it up here. As you do that, we create an angle that is swept right here from these 2 points. When you lay that off, we're going to measure that angle very quickly. Like this right here. And you'll notice you can lay that off right here, here, and here. That's because it's at the third radius. The third radius will do exactly that. You notice also, just for the ease of comprehension, I call this angle 4 loosely. And these trisections 1, 2, and 3. Measure angle 1 is 1/3 of the measure of the total angle created here. We represent as alpha. As you extend this up further, any place along here at the junction of a point of tangency between the circles on the angle bisector creates angles that may be swept down here, and you'll find that this is R1, R2, R3, R4. As you continue upward along this angle bisector, it literally tells you how many sections of equal arc you're going to sweep from A to B, arc AB. Just for your viewing, the original angle is angle AOB at R sub 3, measure angle 4, this right here, okay, is equal to, is congruent to rather, angle 1, angle 2, and angle 3. Okay? 1, 2, and 3. 1, 2, and 3. You simply put this as measure angle 4, this right here, is equal to 1/3 of the measure of angle AOB. That's the trisection. As we continue up, I put this on here just so you see that it works at any radius that you wish to stop at. R sub 5, this right here, that's radius sub 5. Measure angle 5, this right here, is equal to 1/5 of measure of angle AOB. That's denoted here in these green lines. There's construction mark here, there's construction mark here, here, and here. We simply draw from the vertex, obviously, through these points of intersection that you sweep with your compass. It's a very simple construction technique. Again, you have to be very, very, very precise doing this. If you get sloppy at all, you'll be close, but you won't be directly on. If you're careful with this, it'll work out perfectly every time, like it has for me. I would like to thank my dear wife, my daughter-in-law Jody, for help in production, both of them. My two sons, who also have been a wonderful source of inspiration. My geometry class that I had last year at St. Joseph High School in Victoria, Texas. But most of all, I want to thank Almighty God who shared this with me as I lay ill better part of a year ago. May God bless you. May He keep you. May this bring some joy to you from the caretaker of SDG. Good night.